Okay, well, thank you for coming. I'm very glad that Wolfgang is visiting our institute for the second time. And well, he will speak about what you will hear, but generally speaking, it's about those aspects of open questions of quantum mechanics, which still, 100 years later, still cause uneasiness.
Thank you for the introduction. Bienvenidos a mi charla, or restaurants in English. Yeah, so let's talk about the foundations of quantum mechanics. And that's something my group has been working on for the last 10 years. There's a list of students, bachelor to PhD students who were involved, a colleague from the math department, background in stochastic theory, and a colleague from our institute, a lot of discussions, and the ones in blue are the ones who contributed directly to the results that we showed. So why does one continue to work on foundations of quantum mechanics? Just a few citations from the history. So the very famous one, Richard Feynman, from 1964. That was 1 year before he received the Nobel Prize for his contributions to quantum mechanics. Then there is also a very famous saying by David Merman, a very famous quote. Typically one knows this: shut up and calculate. Don't discuss what it means. You know how to calculate things. It's from an essay in Título from 89. I think many people know that quote. Shut up and calculate is very famous. What's less famous is the next sentence of the same essay. It's a wrong chapter. I will go on discussing what's going on. As a last example of very, well, in this case, I mean critical people, Sir Roger Penrose, one of the Nobel laureates, said it's not just one thing that is wrong, it makes absolutely no sense. It's a very strong statement. One may understand how it comes to that, but he's just very critical. No, that's hard to understand if you teach and learn quantum mechanics the way we are usually doing it. Well, I think you start with operator theory, or you start with what Schrödinger did in 1926. He derived this famous equation, which we all use to calculate, describe problems in non-relativistic. He argued this equation into being in 4 beautiful papers in 1 year in the Physik 1926. And his idea was to derive something like the Hamilton-Jacobi theory of classical mechanics, but for the quantum world. That was his goal. And he came up finally with this equation, which we all know it includes and it works perfectly. When he derived this equation, it was not quite clear what was the meaning of this psi, wave function, its physical interpretation. But that was resolved in the same year by the Born postulate. He said, well, the modulo squared of this function gives you the probability to find the particle position, etc. This was a well-defined starting point, and then people worked on bring this together to develop Hilbert space theory, all these things. And then in 1932, John von Neumann published a very famous book on the mathematical foundations of quantum mechanics. In 1932, it only appeared in German first. And so the idea can be summarized in the so-called Dirac von Neumann axioms. We have a vector in the Hilbert space, a state function psi. It evolves according to a deterministic partial differential equation, time preservable, it's a unitary time development. Everything's deterministic in this case. But when you measure, you're not allowed to use it. When you measure, you have to do a projection. So the wave function gets projected on an eigenfunction of the quantity you're measuring, you get a value with a certain probability. And this together forms 3 or 4 or 5, depends on how you count them, the Dirac von Neumann axioms of quantum And of course, this switch here, completely undefined. What's a measurement? There are a lot of problems. So people thought about that, how to define what is measurement. Do I need somebody with a consciousness to do measurement or not? So there were a lot of discussions in theory. So that's the famous measurement problem, which has been with us for a long time. There are two ways out of that, which are one a bit older, one a bit newer. Many words interpretation says, well, the wave function never collapses. The universe just splits the measurements. Infinitely many parallel worlds, all the different results of ERA. That's from the 50s. And then there's the opposite. It says, well, this is wrong. The wave function is continuously collapsing. And it was mostly developed in the 80s. So there's two ways out of this dilemma. There's something more fundamental, a problem around this axioms which define the quantum mechanics we're usually using. And I think this was first discussed or became visible in these famous discussions between Niels Bohr and Albert Einstein, not at the Solvay conference, so that's perhaps the most famous group photograph in the history of physics. Not at a conference, but sort of the breakfast and dinner discussions in the hotel. They were discussing about the foundations, whether the theory as it was developed at that point is complete or not. Einstein said, well, it's okay. We have the wave function, it tells what we know about the system. It's epistemologic. But there must be a reality below it. There must be more. He was not content with the claim that the description that I put up on the last slide is complete. Bohr insisted, no, it is complete, and they argued a lot about it. I think both were aware that saying that this is a complete description cuts off one leg on which physics stood. Predicting the statistics of results was always one part of physics. But explaining how the measurement process created that result was the other part. How that came about, describing the dynamics of the measurement process. Up to that point, it was always a part of physics. And what, let's say, the Copenhagen interpretation and Bohr's discussion claimed that, no, it's no longer possible. This is complete, I can no longer describe the measurement process. That's a big, really, it's a cut-off part, a big part of physics. And he said, it is like that, I cannot do anything about it. As I said, Einstein didn't believe that, and he tried to come up with ideas to show that there can be more. By the way, there's a beautiful book about this. Going to this conference, Chagalupi and Valentini. And but then in the same book on the foundations of quantum mechanics by von Neumann, there's no hidden variables proof. So that's the name by which this extension of quantum mechanics comes with some hidden variables, something more that's not in the normal space description. That line will be a timeline which appears now. This will go on as we talk. So it seems to be decided at that point. Bohr was right, there's no extension. However, 3 years later, there was a paper by Peter Hammer, which showed that there is an error in the proof. It's not a mathematical error, right? But when you want to say it's relevant for physics, there is a logical error that has been done in this proof. 3 years later. However, when she was female, she was completely ignored. Nobody took note of that, except perhaps a few people, but by and large, the physics community ignored it. And at that point, we started to write books about physics, or textbooks, which we used for teaching since 90 years. They all were acting like this has been proven that quantum mechanics is complete. Here it's quantum mechanics. Well, up to a point, some years later, David Bohm, he was actually writing one of these books, and a very good one. He meant to really clearly put down what quantum mechanics is and the Copenhagen interpretation of what it works. He wanted to discuss it with Einstein and tried to send him the book, tried to contact it that I would like to talk to you. And Einstein said, yes, I've read your book, come by. They discussed about that, and after that he said, well, he did the best way he could, but it was not really like the quote from Penrose. It was not really logical, consistent. And then he came up with what de Broglie had thought of in the 20s and what's now called de Broglie mechanics or Bohmian mechanics. You can see it as a way to complete the idea that Schrödinger. I told you Schrödinger wanted to develop Hamilton-Jacobi theory. Hamilton-Jacobi theory consists of an equation, a nonlinear partial differential equation for the action, and the prediction, a way to calculate paths from this action function. You calculate paths by saying the momentum within the other side is just a gradient of this path. You start at some position, then you always go along gradient of these functions. This generates paths which are small. And Bohm said, okay, why don't I do the same quantum mechanics? So particles are there, they have paths, move along, it's generated from the action part. The action is in this exponential, the p factor square. So that's a hidden variable theory. It's in complete agreement with predictions of quantum mechanics, quantum mechanics. And that was puzzling to John Bell. He got to know that in the 50s when he was a young graduate student. What's wrong with that? I see this theory, and then there's the claim that von Neumann wrote a book proving that such a theory cannot exist. That doesn't fit. And you worked on that, thought about it, weekends, in the sabbaticals, in his vacations. So was in his normal life, he had to calculate scattering cross sections at CERN. In 64, he came up with two papers. He submitted 2 papers. So, wrong. In one, he reported the same problem that Peter Hermann had seen 30 years earlier. This proof is just not right. It's incorrect. This proof that there cannot be. But he went on and calculated these inequalities, limiting what type of invariable theory you have, what the conditions are, what the properties. And this, some people say, started the second quantum revolution. So everything coming up from here, from entangled states and their properties, and quantum computing and quantum topography, and everything we have today starts from this behavior of entangled states and from the fact that they are very differently from classical propositions. That's a lot of different. Okay, so you can already see that I'm aiming to go towards something which is, in a sense, an extension from the quantum mechanics, the Hilbert space quantum mechanics. But to motivate this formal extension that I think works, and why it works, let me go back to the year 1927. That's a year in which Heisenberg published a famous thought experiment, the gamma ray method. He said, let's assume we want to measure the position of a particle. The smallest perturbation we can do is scatter a photon. We discuss the scattering process, and you want to make this delta X smaller, you increase the frequency or reduce the wavelength, and automatically you increase the uncertainty in the determination of the momentum. And in a way that the product of the two uncertainties is always half the image. But he invented this thought experiment as a motivation or a physical explanation for the uncertainty relation we are using. commutation between for instance, position and momentum operators gives you a variance in the measurements productive. The variance is as always large in h bar squared. I think this is a beautiful thought experiment. And it has to do with the fact that these objects you want to measure are very small, easily perturbed. However, when you think about the development of quantum mechanics, people always thought about classical mechanics of a closed system, then try to convert that, and translate that into an operator-based theory. But it's always the idea the system is closed. So Heisenberg doesn't throw a photon at a particle, it's completely isolated. It doesn't interact with nothing. But that cannot be true. I mean, quantum mechanics was invented for black body radiation. There is always radiation. No particle, nothing in the world is ever completely isolated. And for the small world, for the particles in the quantum world that we want to study, this matters. As Heisenberg's thought experiment showed. It makes a difference whether you think it's an isolated system or it's an open system. And this is my argument to go to theory that's actually describing open systems. However, it cannot be a simple open system which is dissipated, which we are used to. It must be somewhat more complicated. Unfortunately, there was a guy, Nelson, 1966, who analyzed how to describe a system which is time inversion invariant, but stochastically. So this red line here, so what's in there, that's the physics. That's the physical assumptions. I describe the motion of quantum particles in the quantum world, non-relativistically, the time inversion invariant conservative diffusion process. This diffusion is the next simple thing after deterministic Newtonian motion. It's Gaussian processes. It's a diffusion process, but it's time inversion. The diffusion coefficient is h bar by m. So when the mass gets large, when we go to a wavy environment, this doesn't matter, and you get classical mechanics. And there has to be a sort of a stochastic. So that's this equation here. It's a forward internal equation. There are two velocity fields here. A bit about them later. And there's a noise process, a forward Wiener process, and there's the square wave diffusion coefficient. But the same way you can describe this by a backward process, which starts at some time in the second time. The backwards, the change to the backward process changes the sign here, and you have a Wiener process with slightly different statistical properties. That's the kinematics. That's the dynamics. X of t described that way, and I have to say, in which sense are these the same processes? Not pathwise, but the probability distribution at each time is the same for both the processes. So P of X and t is the same for both processes. You will then have to have a dynamic law to do Newtonian mechanics. Now, these paths here generated are algebraic continuous, but no differential. It's just a property of Brownian motion diffusion processes. So you need to generalize the concept of acceleration, you find some mean acceleration, and just write down the so. Oh, then you go just to the math of diffusion processes, you go to the Fokker-Planck equations that correspond to these larger type equations. And you see that you can write the velocity v, which is the streaming velocity of the probability, as the 1/n times the gradient of the function s. This other here is called the osmotic velocity. It's h power 2m gradient of the logarithm of probability density. This you can easily write. It's just a consequence, a logical consequence. And it turns out these two functions, s and rho, fulfill a set of coupled partial differential equations, which are the Martin equations. The Martin equations are in turn almost equivalent, I call it a ground state to the Schrödinger equation once you define a complex value function just as well. So that's why he called this paper the derivation of the Schrödinger equation from the Schrödinger. That's the mathematical implementation of this idea that you have to treat as an open system. You know, there is energy conservation also in the quantum world, so it has to be time inversion invariant, and you have to have something like the energy of the system is also a stochastic variable, but in the mean in a stationary state it has to be constant. It's not absolutely constant, as it would be in classical mechanics. It's exchanging energy with the environment, but in the mean it's constant. Well, this was a starting point of lots of things that people did. The first 30 years were very active in this. And people came up with, first, of course, you have to do something like a Lagrangian and a Hamilton principle. Final version, I think, was done by Prof. 1995. And put on the sides here what we do in classical analytical mechanics and what I call quantum analytical. Say Nelson took the classical kinematic and dynamic equations of mechanics and formulated the kinematic and dynamic equations of the Newtonian version of this. Then you have a Lagrangian time integral defines action functional. Do something similar here. It's a bit more complicated. It's a complex variable integral, but I'll talk about that in the next slide a bit more in detail because there's a lot of physics in there. And then when you find the optimum path for this action here, you get the Hamilton equations for the cost functions. You get this equation here, the continuity equation for the probability laws I can classify. That's included here. And in the quantum world, that's the modified Hamilton-Jacobi equation. So the equation of the action has an additional term here, which is proportional to h squared by m. The continuity equation also is valid. That is the velocity connected with the flux of probability. You also have Hamilton's equations in classical mechanics. And that's something we started working on, how to derive an equivalent version of quantum Hamilton equations from this Hamilton principle for quantum mechanics. So, since the mathematical structure of this, is really very similar. It's just a basic quantity that's different. Here are differentiable parts of the force. And here are continuous, not differentiable parts. The rest is mathematically really equivalent. You can use the same tools on both sides. So that's why I tend to call this here, all this together, quantum analytical. Now I promised you to talk a bit more about this, this functional Hamilton principle that Prof wrote down. And I said, well, it looks like the classical one, just that the velocity is somewhat older. No, it's a complex value velocity. Here it is again. So that if this IU would be important, this would just be the classical motion. And now you can think of this variation principle not as a like Euler-Lagrange type principle where you search for the optimal path, exactly. But you can think of it as an optimal control problem when you try to find the optimal control velocities V and U. You can do the same in classical mechanics. There's a tool which is called Van maximum principle, 2060, with Triagin in this group in Russia formulated this, which allows you to derive the equations in classical mechanics, to derive the quantum equations. And the physical content of this is that actually it's a very compact way to write down two ideas, two extreme principles in one. The real part is what we would know from classical mechanics, some action principle. Here it's not a minimum action principle, but it's a saddle point action principle, because you have actually two velocities which counteract each other. One tries to minimize it, and the imaginary part is an entropy production principle. So that's statistical physics. So it becomes the statistical nature of quantum mechanics with this principle. Okay? And again, the two oppose each other. You can use that, and the stochastic version of the Pontryagin-Maxwell principle to derive this Hamilton equations I showed you. As a side remark, think about this also. It's a game theory problem. There are two players, U and V player. Play two games, one game, the second game at the same time. We try to find the optimal solution for these two games played simultaneously. And then this is called the logical game theory of these two games. So that's precisely this answers first question my title. What is it? It's this set of mathematical structure. What is it good for? Well, there are several things. I think one of those I talked about the last time I was here, a million times. Choose another example. When you think about what puzzled the people in the development of quantum mechanics was the stability of the hydrogen atom. And it's built stability in S states without any angular momentum, because this you are not expecting from a deterministic Newtonian type theory. Without any angular momentum, our solar system would be unstable. And they knew there are states without angular momentum, but still the hydrogen atom was stable. But when you derive these dynamic equations for the, let's say, the electron or the relative coordinate R here between proton and hydrogen, proton and electron and hydrogen, mu is the induced mass. We have to deal with the properties of the stochastic equations. And one of these properties is that it makes, it has an influence what the metric tensor is. If it's just a one, trivial identity, you don't get any effects. But already when you write down the metric tensor in polar coordinates for the hydrogen atom, it's not trivial. It's a non-trivial tensor. And this non-triviality makes additional terms in the equations of motion for the variables in the polar coordinates. For the relative distance between proton and electron, you get this additional term here. And for the velocity change, the change of the relative distance, you get a term which exactly looks like the centrifugal barrier. Creates a centrifugal barrier just from the mass of the stochastic dynamics. And this tells you that this is a stable thing. It does not, the electron does not collapse with the hydrogen atom with this dynamics. And you can, of course, do simulations of the paths of the particles. These are two paths in the one S state. They never vanish, they are stable. And this would be a path in the px state. There's a node here separating these two regions of stochastic processes. You see they can never cross nodes. It's a different part of the same story. You see, it's an easy answer, not an easy answer, but it's just a mathematical consequence of the way you describe this system that the hydrogen atom is stable in the S state. It's not astonishing. That's a more recent application. There's a beautiful, there are many beautiful experiments. The one I took here is from Markus Astelmeyer's group in Vienna. They take a silica nanosphere, it's almost 150 nanometers diameter. And they put it into the focus of a question.
Remarkable about that in quantum mechanics, if you put an electron stays still.
It says that, yes,
so,
yes.
So it's nice to get.
Thank you. That's one of the big differences between Newtonian mechanics and this here. Newtonian mechanics in the S state, stationary state, with S equals 0, the ground state. You put the electron at a position, it never moves, it stays there. So you have to always look at an ensemble of electrons you put there with the correct probability density, then you can produce it in later. This here is different because we have this additional velocity, it's u, which keeps the probability density intact. And therefore, particles actually move around, and with time you can get probability density you see in the ground state. So this here is a levitation experiment. So this sphere here is kept in the focus of a laser beam, and there are some additional scattering is done, some Rayleigh scattering for the position and Raman scattering for the momentum, but you can levitate it here. So this is a particle with 10 to the minus 18 kilograms of mass. Big, mesoscopic, nanoscopic, 150 nanometer particle. And they measure the position and the momentum, they measure position fluctuations and the power spectral density of position fluctuations. And a lot of focus here, this direction is shown here. So the case, this blue line here gives the oscillator frequency, this direction, and then there's some residual noise in the experiment. They have position correlation. I told you they may also measure position and momentum, so they can actually make phase-space trajectories. Here's a green one, which is a cooling process, and then there's this somewhat light blue one here, which is the thing they can do, energy they can do down to. The dark blue one here, the 0 point fluctuations. So they cool down the motion of this particle to about 0.5 h bar omega above the ground state. It's almost ground state motion of this rather heavy particle. It's big quantum motion of a 100 nanometer big sphere. But since this is not an integer number of phonons in the motion, it cannot be a stationary state of the harmonic oscillator, it must be a coherent state. Coherent states can have every energy possible, they are exact solutions of the harmonic oscillator. And so, if this is a coherent state of the harmonic oscillator, we can write down our equations for the quantum harmonic oscillator, quantum Hamilton equations. They just possess the coherent states as exact solutions. And this is just a coherent state for stochastic motion with some classical path, and in addition you add the ground state equations. You can calculate the position correlation function and that ground spectral density analytically. It's such on here. The delta function is absent if you have a finite time horizon. And if we shift it to the background noise level, the experiment has, I don't have experimental data unfortunately, but you can see that this case with the background noise at the same point that you see here, and it's the same units here. So there's no adjustable parameter, we know everything about this. And also if we say, okay, now when you cool down thing, this particle is just a damped harmonic oscillator plus the quantum fluctuations. We get the green parts. Compare that to the physics. Make a few predictions about how you can measure this number of Potter in the beyond the ground state from the probability distributions. So this is one of the applications that work for this. So let me get to the final part of the talk. I think we time for that. A more complicated thing. Spin. Spin is a really crucial property in quantum mechanics. When it was formulated, or it was invented that much, but came out of the Galler experiment, or I don't know, it's Zeeman effect. There was an idea by Martin-Luther-Universität to describe it as the eigenrotation for charged ball. A simple picture from classical physics. And that is a charged sphere. There's an axis. Rotate around that axis with a magnetic moment. It's the magnetic moment, the experiments interact. That's an eigenmagnetic moment. Of course, once suggested in the literature, and actually they were not the first to think about that. First was Koenig. At that time, he was a postdoc with Pauli. Pauli said, think about the size of the object. It has to rotate faster than the speed of light on the surface. So this cannot be true. So Koenig never published it. So the fame for this description went to Wolfgang and Gauss. That was Pauli's argument that you cannot do it. With deterministic mechanics, you will have a velocity which is larger than the velocity of the surface. But we have a different system here, we have a different mechanics. We don't even have a well-defined velocity, because that's a derivative of a path which doesn't exist. So we think we can go on here, thinking about it in this simple way. Actually, this was analyzed also in a nice publication by Wolfgang in 1950, to do some mechanical model for this spin. And a student of Nelson published the kinematic and dynamic type of equations and showed that this works out with the behaviors of the target also derived. It's Schrödinger equation, Schrödinger wave function, which depend on the position of orientation. These match up the stochastic description of this. So what would be the idea? Well, all these functions, especially also wave functions, are defined in configuration space. Configuration space is the tensor product of R3, the transition degrees of freedom, and SO3 for the rotation. SO3 you parameterize by the Euler angles. There's two angles which define the orientation. It's a little vector here, it's the rotation axis, and there's another angle which tells you how much you rotate on this axis. The classical Lagrangian look like that, except you forget the q's. Kinetic energy of translation, the coupling to the vector potential here, the coupling charge to the potential, with the kinetic energy of rotation, the coupling of the magnetic moment of the particle in the rotation. I've shown you that you go from this to the quantum world by just make a little q index, understand it that instead of v, we have to subtract some osmotic kind of velocity, both for the rotation and for the principle. That's the Lagrangian. You feed the Lagrangian into the mathematical apparatus, which is this chemical principle, solving it with the maximum principle. And you get out equations for the dynamics, make equations for position, for the angles, for the translation momentum, and for the orientation of the canonical momentum. I only wrote down the ones for the angles and the canonical momenta for the Euler angles here. The other ones. Again, because of this being not a flat but a Riemannian manifold, you get a complex, more complex metric with additional terms. The equations of motion, this is one of those. This is another one. These are additionally, you have some matrices here which lift the noise process from the this flat space here on the SO3. And you have matrices here which are occurring in the mathematics of this particle control as additional adjunct processes to the processes you study. And again, these are depending on all degrees of freedom. The equations are written down here for magnetic field in z directions, so y phi is just the angle rotation on the z-axis. And so in these equations, the internal rotation is just once, the rotation of the z-axis is just once. There's no torque on the z-axis. There's a torque for this polar. Important here is there's a coupling between translation and rotation through these stochastic matrices. They are functions of the coordinates and positions. These matrices. Now you have dynamic equations. I didn't show the ones for the translation, just for the rotation. But now you can see what happens to a particle which has charge and magnetic moment and moves into a magnetic field. How is it reflected? What happens? That's actually what you do in a standard. That's the classical setup here. You have some beam which is produced, it enters the operators, and instead of showing a continuous reflection, they are just it's a spin 1.5. We can do the same. I'm going to just show a special application. Let's just show a polarized beam. So we have one of these things, and you just take the upper one and you feed it into the next one. There's a certain aperture here with which the particles enter this magnetic field. And then there's a certain angle, it's pi over 4 here, we move the first and the second step. For statistical selection of starting positions here within the aperture, and then you see these particles deflected and the magnetic moment reoriented towards the new direction of the magnetic field during the crossing of the magnetic field and afterwards. So this dashed line here is the size of the magnet, and 3 centimeters, and there's 6 centimeters to the screen. This is actually here is the magnetic field, and here it's it's beyond. So when it's pi over 4, most of them go in the direction, few go down, and it's pi over half, it's up. So that is Sx, and we have polarized in Sx. That's what you would expect. And of course, you can look at that as a function of the angle between the two tangent operations. The points here are from just simulating paths of our dynamic equations for the points. 10 to the 6th paths per point. The dashed lines are predictions from Hubert's Pauling. It's exactly it is. So exactly reproduce what you would expect from quantum mechanics for this type of experiments. But you can see the particles moving and see how they reorient. Now there's a difference to what we normally do in quantum mechanics. Spin here is not an internal degree of freedom. Pauli postulated it at some point to be an internal degree of freedom. The simplest thing was to have just this element of C2, so you have up or down, and you have complexity position of that, and you can calculate everything. The only thing you can calculate with that is this here. Because it's not, so your spin in this way is not in the real world. It's nothing that's in our world. It's some C2 Hilbert space. But the magnetic moment is in our world. The thing we are interacting with in the experiment is in our world, not in the C2 Hilbert space. And that's what we did with that. We brought this back to our world, and then it's not a property that this thing brings with it, like a membership card, you up or down. But it's a dynamic property which evolves in time. Magnetic moment reorients because of the action of the magnetic fields. And then here the statistics is the same that we calculate in Hilbert space theory, as it should be. Because Hilbert space theory is just this MBA version of this dynamics, this quantum analytical dynamics. So everything you can calculate there should come out with this extension of quantum mechanics also. It's not a replacement. It's an extension of it. And it does. We get the same statistics, but we get a dynamic description of the measurement. And then, of course, you go on. Now we have two standard operators with Alice and Bob. You start with a singlet state of two coupled speeds, two coupled magnetic moments. It's the Einstein-Podolsky-Rosen-Bohm thought experiment. It was always a thought experiment because that cannot be realized in real experiments. In real experiments, you have to go to linear polarizations of photons and do this with photons. That's the way that because the assumption is that you just produce here this singlet and then they fly apart and they don't interact. There's nothing that interacts with anything else. Of course, magnetic moments in real space will interact. They do interact when you try to do it with real particles. So they fly apart, and then Alice and Bob can select their orientation of possible. What's special about the singlet state, also this works also for arbitrary independent states. What's special about the singlet state is that it's perfectly antiquated. So whatever measurement axis Alice and or Bob decide to inquire in the end, the result of both experiments will be perfectly antiquated. There's a strong restriction on this dynamic quantities, this v velocity and the u velocity that are dynamic equations, but they just follow from building up the correct singlet or triplet or whatever states of these two spins in the quantum description. So we can write only dynamic equations of motion, and we can simulate. And so here is just a plot of the measurements when they both are with respect to some arbitrary z-axis tilted by pi over 4. Both Alice and Bob. This is Alice, this is Bob. But you can see from the color code there are just a few examples that dynamics in the standard operators is perfectly. This just gives the average spin projections. More information. Now, this is a function of this angle delta. There's one way of formulating the spelling inequalities, which says that the probability to find plus when one of these two is at 0, minus when the other is tilted by delta, plus the probability to find plus, the first one is tilted by delta to this arbitrary z0 z-axis, and find minus with the second one, the 2 delta, must be larger or equal to probability for plus at 0 and minus. Just one way to then derive. And this should be true for delta smaller than pi. Well, as I said, it's rather arbitrary to say what is the z-axis. So actually, this here and this here should be the same. The first one is, let's say, the green, and the other one is the pink one below it, and you can basically not even see it. There are two functions here, the pink again, magenta one, and the green one, which is super. The sum of the two is the blue one. The sum of the two should always be larger than the black one, if this would be a classical theory which fulfills certain requirements. That's the value. You can see when they just simulation results, we simulate these parts from joint measurements for the two different orientations of the vortices. The black curves, the lines are again from the special mechanics. But the quantum mechanical result violates the dynamic quantity. We know that. That's the Nobel Prize. And that we did produce exactly to calculate. But we have to pass it. You can see them here. So let's come back to the timeline. I already said there's was a set of beautiful experiments over about 50 years. Clauser, Speck, Zeilinger, their groups. Really beautiful. In 2022, they received the Nobel Prize for really showing the world quantum mechanics, not only the quantum mechanical calculations, the real world also, the real world in this case being polarized photons, violate. Really wonderful. Unfortunately, the laudatio of the Nobel Committee is less than wonderful, but it just contains wrong statements. The black one here, this states that if there are hidden variables, the correlation between the results of a large number of measurements will never exceed certain value. When we look at Bell's derivation and assumptions, doesn't say that. And also this means when we place my theory with the hidden variables, I can agree with that. I don't want to replace them. Different quantum mechanics is correct, we all know that. But I can do more, broaden the scope, the mathematical scope of mechanics. So what they got wrong, I don't know whether any of them ever had the frequency. Bell's theorem states that the correlations cannot be reduced by what is called the Bell's separable. Some people call it local hidden variable theory. Separable in this case means that the probability for finding two properties for this, let's say, particle A and particle B, factorizes into probability to find probability for particle A times the probability to find probability for particle B. So 2-point probability factorizes into the product of 1-point probability. In statistical physics, mathematics, we call that statistical independent things. But these two particles are not statistically independent. I told you that we compare them in a state where they are completely antiparallel. Now, this is a state with zero angular momentum. And angular momentum in physics is a conserved quantity. When you do not act on these two particles, they will be always anticorrelated, however long you wait. Because of the conservation laws, the probability of finding results for the two particles never factorizes. It's the same for the old Einstein-Podolsky-Rosen experiment, just for translational momentum. Physics has conservation laws, so you cannot assume that this probability factorizes. And therefore, we can reproduce just with our classical. It's a classical simulation. We can reproduce a violation of empirical properties.
Only what we talk about are the measurements. Have to correlate the measurements in another way to make this correlation.
No, that's the typical interpretation. It's locality. But actually, what is assumed in Bell is only factorization of probability. I have an additional slide. So there's no strange thing about this. In a sense, there's some of this non-locality in our equations because they depend on the positions and orientations of both particles up to the moment you measure. Because then you change you break the correlation. When you start measuring on one particle, you break the correlation because you change its angular momentum. It's no longer conserved. It's different. So back to those two guys, Bohr and Einstein in 1937. From what I showed you is we would answer that this question, is there reality below it? Yes, I can assume particles, corpuscular objects, moving through space with a conservative diffusion. And if I do that, I don't violate any assumption or any properties of quantum mechanics. In fact, I can derive Hilbert space quantum mechanics for that. But in addition, I can look at things like how long does it take to tunnel through an area? How long does it take to particle from here to there? Which I cannot do in Hilbert space quantum mechanics. So there's more things one can do. And I showed you that we don't have a measurement problem because we described the measurement process, something that was declared impossible by the standard interpretation. And this claim of impossibility was, let's say, rather primitive, because we just constructed it in a way and showed that we can do it. There's nothing strange. There's still a lot to do. First one concerns density function theory that is based on something that I haven't shown you here. It's these functions that is Hamilton principle we use, this ground state equivalent of this variation principle. This variation principle is the basis for the Cohn theory, which again is the basis for Kuhn-Charm wave density function. We should be able to do something similar here, starting from our theory. And of course, we need to extend that to Minkowski space, relativistic description. It's completely lacking. We don't have. There are some people who try to write it down, but I don't quite understand that yet. And I have to think a lot about how to do that for Galilei space time. One thing that is known is you cannot have Markovian processes in Minkowski space. We need to go to phase space. Description there. So there's a lot of open questions. And finally, it's a bit, well, in the sense, you put in quantum by saying, well, the diffusion coefficient is h bar n. That's your background, kind of coupling to the background. Where does that come from? The diffusion coefficient in our equations is this point. Why?
All processes are not linear. It's not about just a particle, particle separated. I mean, this H bar is something that is universal.
Yes, that's also a good thing. Why doesn't it change with temperature or anything like that? There are some arguments. There was a paper 30 years ago which argued for that, but it's not so really convincing. And I think the reason is that it has to start with this coupled Lagrangian for fields and charged particles. Derived from there by projecting out the field degrees of freedom just to that, I think, is the background. To derive it, nobody has done it. Lagrangian is there, people have worked on that. As you see, the normal when we do electrodynamics, we are sort of a bit schizophrenic. We have two equations. One is the set of equations. Maxwell equations, you assume that particle density and particle currents are given to calculate the fields, and you have the Lorentz equation for quantum mechanics. So you assume that the fields are given to calculate the particle trajectories, but actually both have to calculate at the same time, self-consistently. That's the complete solution. my assumption is that's a hypothesis. Once you do that, you may be able to derive this type of dynamic data. But this is a big. Thank you very much for your attention.
Perhaps I misunderstood the approach, but in some sense, I understand that you are considering that the quantum system is always open, subject to some noise. So with certain characteristics. So in my Copenhagen interpretation of entanglement, I put, for example, one electron up and down in a symbol. And then as long as I don't measure, I can move it around the universe one electron one side and the other. But in this picture in which the system is open, I might think that would be like a, suppose I create a symbol and then I try to put them very far away. Since now these both systems are open, these are sort of like an effective length at which these guys stop being correlated or something like that.
Yeah, I understand your question. It's a very good one. I mean, you would assume that there is some correlation time or correlation length where this
something, because if the system is open, I would have come. I'm trying to think of an experiment, right? Whether we could test the point, there should be like a, and since the coupling is universal,
yeah,
perhaps you can.
The strange, well, a bit strange thing is that you can actually for these single state, you can derive it from the description of the single state. The deterministic factors occurring in the equations of motion are such that this anticorrelation perfectly exists. It doesn't decay. With everything with respect to every axis. It doesn't mean that they are not moving around, but the anticorrelation persists. There is no decay time or anything. It was surprising for us, but it just worked out that way.
And you hope that, okay, perhaps my example is too simple, but would you hope that for more complex states or something I could, in the end, have a correlation length or decorrelation time?
Well, actually, if one could do these experiments with particles, which one cannot, because you never make them non-interacting. If they are correlated, they first have to interact. And when you have just Alice measuring something, she changes the orientation of this magnetic moment of the particle. At that point, the perfect correlation between the two particles breaks down. What I've shown you is simultaneous measurement. So this particle just does its own thing from them, because once you do that, you are not allowed to use the velocities, this v and u any longer, or the entangled state any longer, because same as the wave function, which consists of probability density and action, also the velocities are epistemic quantities. They are not in the real world. They reflect all our knowledge of the system. And once you change that, from that point on, this other particle will just do free diffusion because there's nothing wrong with it. So if we wait long enough, we should break the correlation. That would be a prediction. But since you can do the first part, it's so far as not possible. It's different from the photons because the linear polarizations don't have an intrinsic dynamics. They just stay that way. So with photons you cannot reduce.
Why do you say that the system is open instead of saying that the system has an intrinsic noise and that is the quantum?
It's not an intrinsic noise, it's a noise due to the coupling to the environment. So it's not a property of the system, it's a property of the interaction between system and environment.
To see what is okay, you have environment. This model works as if we give a local environment. So the environment acting on one particle should be the same that the environment acting on another particle in Mars.
Yes,
So,
H bar is the same everywhere.
yeah. And the other thing is, if you really have noise, this dynamic is real by noise coming from the environment. Another momentum should be considered.
No. You see, that's something that the theory of one motion is old. Einstein and Skolachowski and all those people, Langerer, they always, in Wiener process, mathematization of that, it's always dissipated. It's always a dissipation. Now, when Nelson started, actually, I think he looked into that when he thought about the depleting quantum field theory in the 60s. He saw that he got stochastic fields. He started to think about quantum motion and recognized that he can formulate time reversible quantum motion. Strange thing, conservative. When you look at the equation, you derive the equations for an n-particle system, you get the same expectations, so it's the same conservations as for a classical n-particle system. So average angular momentum, average momentum, all these are conserved.
Lower. Locally, I don't know, because some parts, one part of one direction, or part of another direction.
If you don't do anything with that, they will always be conserved. Same as for classical mechanics. You can even derive that. It's just a property of the equation of motion. So say, yeah, the expectation value of the momentum. Instantaneous value can fluctuate.
The individual measurements, if one electron, another electron, do the experiment, shift the result, then do the same another time. Many times they have correlation. And I don't know in this case, this conservation work for each pair of events.
Well, not 100%, but you see what you measure is not an intrinsic property of the electron. Like the spin is not an intrinsic property in this case, it's the magnetic moment is changed by the measurement process. And what you see in the end is the correlation, whether the correlations you're looking at is not the correlations at the end points of the correlations, but at the end. So where does it end up on your screen? That's the correlations that you compare. And these are maybe not 100%, but highly articulated. Even if it's individual. We saw all the paths were simulated when the one goes up, the other one goes down. Because at the same time, they enter it with opposite orientations of their moments with respect to the field that's random, but in the opposite half sphere. That drives them to the opposite direction.
It's the model for the spin. It's kind of
Very good.
how do you spin for
Also a good question. The equations of motion, you could put them down here. But in a sense, that goes back to the description with velocity fields or density and action on R3 times X. You only get well-defined diffusion processes for either spin 1 or spin 2 systems. So when you don't have them, then the fields are not well-defined on your punishment. So you don't know that the electrons want, but in the end everything is 1/2, which has a mass. That's why we call it and you have a less mass, it's bigger. And so this is, yeah, but you don't know that it's 1/2. When you put that in as a mixed value,
Thank you.
out of the zone. It was out of the zone. Yeah, I know. Theoretical.